So let's get started, everyone. So welcome back. Yeah, so let's so today in class we're going to be looking more at discrete random variables and looking at some like before we've been describing them kind of like quite at like a low level, and we're going to be looking at some common models of them that are useful, that like actually show up in modeling things a lot in practice. Yeah. And so okay, so let's see. So on the schedule today, let's see, so probably the most important thing is, so homework 2 is due, right? You probably know that's due at the end of the day today. There's been, so some good questions on the Canvas discussion board. So there were some points that are probably common points of confusion. So if you haven't looked there yet for possible answers, that's like the first place to go. If not, hopefully you've been going to some help hours. I think the last help hour list on here was was Anna, and also I will be staying for a few minutes after for a while after class. All right. The other thing you probably saw is we posted the grades for homework 1. The grades were not as high as I had hoped. So I'm not the one who went through all the homeworks and graded them, but I did spot check a number of them. So my impression was that most people, who I spot checked, even if they didn't get like above 90%, had a pretty reasonable understanding of what was going on, but they may not have always carefully answered the question. So I feel now that you see the rubric, what you got off for, hopefully that's mostly pretty clear. That probably won't always be the case, right? So the appropriate thing to do then, if it's not clear, is to try and understand what's going on. Like the help hours of myself for the TAs are a great place to ask about that. If you think that something was graded like incorrectly, or you think you have a fair interpretation of the problem which is different than how it was graded, there's you can do a regrade request through Gradescope. We are responding to a few of those now, and we're working through some updates to how things are graded. Okay, but if you see something you think is not right, you should do a regrade request through Gradescope, and we are addressing this. Okay, but something else I saw is not everyone, I think, got points off because they weren't as careful as they probably should have been in answering the homeworks. I expect the homeworks you should have at least a week from when we hand them out to complete them, and you should be able to take care to answer all the questions. And these are things that, like on the quizzes, you should be able to answer them kind of quickly, and quickly get the answer. We'll try and be quite forgiving on the quizzes if you make a numerical mistake in adding something. That's not the main point of the quiz, and we'll try and give you credit. On the homeworks, we expect you to be careful. If you're going out after you graduate and you have a job and you need to do a calculation for something, then you should make sure the calculation is correct, right? You should check, okay, if I have a bunch of different probabilities for a space, they shouldn't add up to more than 1, right? These sort of mental checks. So we're kind of looking for you to have done that inside the homework. That's the sort of thing we're expecting in the homework. Yeah. We are not planning to specifically post solutions to the homeworks, but we will be around in the help hours, and if there's a question of how to solve something, we're happy to go through it and show you exactly the solution then, right? But we're not planning to just post exactly what the solutions are. Yep. Yeah, I think that was a miscommunication between me and the TA, and he mentioned that. I said, that wasn't actually the plan. I guess he didn't correct that in the announcement. Yeah. Yeah. So, any other questions about that? So, I would suggest this was the first time we've went through the cycle of like grading a homework, and there were a few things we did, new things on our side. We hope the next time is some more efficient. Hopefully they're out, you get the grades a little bit earlier, maybe at the end of like the previous week. But so there were so kind of a couple delays, but I wanted to make sure they were posted so you could see them, and you can kind of take feedback from what you may have lost points on homework 1, and before you are completely done with homework 2, that you might have a chance to kind of see, hey, I don't want to make that same mistake on homework 2. All right. I think a lot of you are capable of turning in assignments that would get higher grades. So just to be clear, I think the average grade currently on Gradescope is like 82%. So it's not horrible. I could have that as the average class grade at the end of the semester, and it would be kind of acceptable, but I'm hoping the class does better on average than that at the end of the semester, okay? So we'll hopefully all work together. I will help kind of instruct you towards kind of understanding material and figure out how to answer questions, and you will maybe add a little bit more care on the homeworks, and I think the average grade for the class will increase. All right, so that's the hope. All right, but that's work from, both on my side, from, making sure everything is clear what we're asking for, and also your side, and increasing a little bit the level of care in your answers on homework. All right, and there are a number of people who did very well. I think on a whole, the class did pretty well with understanding, but I think you can be a little bit more careful on turning in the homeworks. Okay. One other thing, homework 3, we're going to post soon. We have kind of we have a draft we have in place for homework 3. One thing we're planning to do is to ask you to do some fairly simple things within R. And so the lecture on Thursday is basically going to be going through those things in R. You'll see it's so pretty straightforward. But in the homework, again, the homework will have this piece of paper. You can write on it in a tablet or edit it on a computer or print it out and then take a picture or scan it to turn it in. We're going to ask you to plot something in R, okay? And I need you to get that in the homework. I think probably the easiest way is to somehow get it, either keep it on the computer or scan it, and then do a kind of edit the PDF and paste something into the PDF before you turn it in. That's probably that's what I think the easiest way if you are, trying to print it out. Does anyone kind of foresee that as being like a huge challenge to do? I don't think the R itself will be hard, right? I think the R will be pretty straightforward for you, and you'll get like an image of a plot, and you'll somehow need to get that into the PDF you turn in. Does this seem like a reasonable thing to be able to ask you to do? Yeah. My intention was that it would be on top of the page in the PDF. So, yeah, I mean, how it's going to be is you're going to have, one page in the PDF, and it's going to have two parts to the question, and the bottom part is going to be write this probably one line command. It'll create this plot, put the plot in there, right, inside the actual PDF. Does this seem this seems reasonable to do? You all are CS or like ECE majors. I figure you can figure this out. Okay. If it's too hard, we can create a separate page that everyone has to upload. I think that's going to lead to more confusion, honestly. So, all right. Okay. So we'll try and we'll release that on Thursday. If you have problems doing that, ask the TAs. There are a number of free programs that make this pretty straightforward. It should take just, like 1 minute to do it, right? All right. Yeah, okay, great. Yeah, we're not planning to post the solutions to homework in the chat, but we're going to, help hours is a great place to ask, and we'll give you the solutions then, but we're not going to put them on the internet. Yeah, so, okay. All right. Okay. Okay, discrete random variables. So let's quickly just review what these are. Okay, so we're going to start with a sample space, right? So the sample space is the kind of the space of all possible events, or the outcomes that might occur for like a random process. All right, and a random variable, okay, x is going to be a function from the sample space to the real numbers. Okay, so think of, I've got a die, right? So like a like a six-sided die, right? Okay, and so you're going to have that the sample space, the six-sided die, is going to be the numbers, the sides, 1, 2, 3, 4, 5, 6. Okay, and the function from an element of the sample space. So this would be like if like a mega was 1, it'd be some value. Okay, so I can map these to so any value I wanted. It could be something like the square of these values, right? So like you get to play a game. It costs you, let's say, so $5 to play a game, and I'm going to pay you the square of the dollars and the square of the number that you roll, right? So if you roll a 1, you get $1. A 2, you get $4. A 3, you get $9. A 4, you get $16. A 5, you get $25, and a 6, you get $36. All right, okay. And so X tells you the kind of like the outcome. It's a mapping into some values. Okay. So, and we're going to, it's a function from the sample space to this value, but we're going to treat it we're going to use X, we're going to use X like inside of equations. Okay, so we'll use it so equations, we'll do stuff later, like we'll do 2x plus 3 equals, like y. Y is going to be another random variable as a function of the random variable x. So we'll treat it like a variable, like you would inside some calculations. All right. Okay, and then there are kind of a couple of important quantities associated with random variables. One is the probability, so density function. Okay, so the PDF, the book in Some other places might call this like probability mass function. For discrete, so random variables, this will be a function lowercase f. We'll use lowercase f for this when we can, in particular lowercase. If we need multiple functions, I'll take another lowercase function close to f in the alphabet, like g or h. Okay, and f of a, right, for some value is going to be equal to the probability that x is equal to a. Okay, so this is the probability, so density function. Okay, and if it's a probability, so if I sum over all possible values of a for f of a, then this should equal to 1, right? So that's a function of a probability. Okay, so that means, and that means all of these values are between 0 and 1, right? The probability can only take a value between 0 and 1, and if I add them all possible values of a, I sum them up, they should be equal to 1. Okay, so the event that x is equal to a, those are disjoint events from x is equal to a prime for a not equal to a, right? So I know by the kind of the law of, so total probability, I can add these up to I can add these up to, so 1. Okay, the other term is the cumulative, so density function. So this is often called the CDF. Okay, and this is going to be, I'm going to use so in uppercase f. Okay, oh yeah, and if I have for a particular random variable, I'll write a subscript x to make clear it's for that particular random variable. Now for a value a, I'm going to have, this will be equal to the probability that x is less than or equal to a. Okay, so it's all the values. The important thing about the output, the real numbers, is that I can apply a comparison operator. Okay, so if I have a quantity a, I can say all the values in the outcome of that the random variable could take, all the values of a or so less than a. I'm going to add all those up, right? So this is equal to the sum of a of kind of, let's say, b less than a of f of x of b, right? So I can take all those values of x, all those values b that are less than or equal to a, and I look at the PDF and I add up all those values, right? So that's what the CDF is. Okay, can draw a picture, okay, where these are the, so this bottom part of the line is the real values, and there are certain outcomes or kind of values I can take, let's say 0, -1, let's say 1, 2, 3, and I could think of having a value of, so from these discrete terms up to some sort of height function. So if a is equal to -1, I'm going to get this height. Okay, so this will be yeah. So in green, this will be the probability that x is equal to a. Okay, and so this will be f of x equal a. This might be 0.1, might be 0.2. Think of this value 0.15. let's say 3. How many do I have so far? 1, 2, 6, 7.5, and let's say 3 has a height of 2.5. Okay, 0.25, 0.25. Okay, so this could be the PDF. This function is only evaluated at these 5 values, and this describes, so, f, which is the PDF, okay? Then, there's also the CDF, probability that X is less than or equal to A. Okay, I'm going to try and draw this now. Okay, so it starts off low down here. It at -1, it jumps up to a value of 0.1, which is where this is. It stays that. So if I'm at a value minus 0.5, well, 0.5 doesn't have any kind of value at the PDF, but -1 is less than that. So it stays as a step function. It increases up to here at 0. It increases not just to 0, but the value at the PDF at 0, but also the value of everything before it. Okay, and that stays as the step function until here. Now it's increasing again by some amount. Here it's going to have a large jump, and it's off the top of the page. Okay, what we're going to do is we're going to erase a little bit here. Okay, and we're going to say it's going to have another jump, and then it's going to be at 1, right? So at the top here, it's 1 and it's 0. So this always goes from 0 to 1 as so like if I evaluate the, if I evaluate f, right, which is this function, so if I evaluate this at an arbitrarily large value, right, you can't evaluate at infinity, but something approaching infinity, it's always going to be approaching 1, right? So f, say f of, in this case, 100 is going to be equal to exactly 1, right? So all the probability it's less than or equal to 100 is 1. That means it's always the value x, the random variable, always takes a value that's less than 100. Okay. Okay, in front, yeah.
So X has image or range. How would you like us to denote that range? Like omega with a MRSA on top, or omega with a X subscript?
So X has a
random variable.
Right. So yeah, so X has its range, right? So all that's important is that the range is contained within the real numbers. Okay, right. So it's so in sometimes it's only going to be like we'll talk about some examples today which are going to be positive integers, right? These are going to be so like some common examples, but kind of later on it's going to be convenient to do things like this where we're kind of adding and subtracting, right? And I could do something like 3.1 or something, right? I can add other values to it. I can like subtract values, and now y is a random variable where its range is going to be different than x's range, right? And so I'm not going to worry so much about exactly what the range is as long as it's contained within the real values. Is that?
I was just thinking how you would label X. It would just be like maybe X of little X.
Well, so these are the values A, right? These are the values A it takes. Whereas like, oh wait, no. These are, yeah, so these are the values A that the random variable is taking, right? So these are, in this case, this is the output of that function is on the x-axis. These are the values that x can take, right? So there's another function which I drew, I illustrated kind of here, okay? And now so the part that's in the domain of X, which is so like the sample space, right? These would be like little omega, right? This little omega is an example outcome. It's a possible outcome, right, of the random process I'm so considering. And then I apply a random variable, right? When I think about a random variable that lives on that sample space, it maps it to these values.
Would maybe be like X.
Right. So if I were to think of evaluating the function on its argument, that's how I would write it here. But I will typically not write it this way. I'm just going to use it like a variable. Think of the point of this mathematics, like mathematical notation, is for convenience. I want to be able to do things like in that green expression, or do things like this inside of, so the definition of, so like the CDF, where I say X is less than or equal to A. I want to be able to do a comparison operator, and I'm not going to carry around this extra notation that it's like I'm applying this on some particular possible outcome omega. I'm just going to write X, right? So I'm defining it as a function because that's actually what it is, and that's the right way to kind of explain to you what it is. But I'm going to treat it like a variable I don't know the outcome of yet. I'm just going to write X. So that's how we're going to use it kind of going forward. Yeah. Yeah, so I'm not doing a comparison on the sample space. I'm doing a comparison on the values that I assign to the parts of the sample space, right? So that if you look at this example, I rolled a die, I got a 4, the value I got was 16. 16 is an element that is one of the real numbers, and I can do, so comparison, 9 is less than 16. Because these are in the, these are in the real numbers, I can do a comparison operation on these. The sample space may not necessarily have a comparison operator, right? That's the left column. The right column has comparison operator, and that's what I use for the CDF. Yeah. Yeah. Yeah, that's fine, right? I could have that 3 also map to 16, right? Well, then I could still say the probability, it's going to change if I ask what's the PDF of 9, it's going to go to 0 instead of 1/6, right? That's fine. I went through an example on Thursday last week where I did this. Like, if the sample space is a sum of 2 die I roll, there are multiple ways to get a sum of, so 7, right? There are a lot of ways to get the sum of 7, right? This is a kind of a simple example where everything, all the values of the random variable are, it's 1-to-1 with the with the sample space here. But for other sample spaces, that's not the case. All right. Yeah, okay, great. Okay, so this was a review of what we talked about on Thursday. Let me talk about, now I'm gonna kind of go through kind of the 3 most common discrete, so random variables, okay? And we're gonna kind of, we'll see that these are useful, and you will kind of, in the homework that's going to be, so coming out, you're going to be using these to solve a problem. To kind of answer some questions, right? And then you'll see that they involve some calculations which maybe you don't actually want to do yourself, and R will be useful for doing those sort of calculations. All right. So the first random variable is the first useful distribution is going to be a Bernoulli, so distribution. All right, and so Bernoulli distribution is going to correspond with a Bernoulli, so a Bernoulli random variable X, okay, and this is this is going to have a and so this distribution will have a parameter P, which is going to be in 0, 1. Okay, and so I will describe this distribution and this random variable by its PDF. Okay, so if I have the PDF, I can do this trick where I add up everything less than a value to get the CDF as well. But this one will be simple. Okay, so this is going to be f of x, right? The probability that the random, this f of x1, this is the probability that the random variable x is equal to 1. Okay, that's how to interpret this. Remember, this is the probability that x is equal to 1. This is just going to be p. Okay, there's some parameter p. I said there's this parameter p, and that's what this is going to be here. Okay, and then I also need to define that's not the only thing value can take. It can also take on the value 0. Okay, that means the probability that x is equal to 1. This is going to be equal to 1. So 1 minus p. All right, so, okay, what if I write f of x equals to 2? What is the answer for this going to be?
0.
So 0. Okay, great. Great. So why is it 0?
Because you've already sequestered all of the probability in p and 1 minus p.
Yeah, right. So I have to have this property that if I add over all values a, f of x of a, this has to be equal to 1, right? And the values f of x and f of x for any a has to be in the values between 0 and 1. So I can't do anything funny like adding, like a negative value and then adding a positive value that cancels out to 0, right, in order to get the sum. And I already know that f of x of 1 equals to p. F of x 0, that this is equal to p plus 1 minus p, which is equal to exactly 1. Okay, so I already just those values 0 and 1 gave me everything, right? So this is it, right? So I can write for any value other than 0 and 1. If I evaluate the PDF, it's going to always give a value 0, right? So all I really need to care about is this, right? So f of x, the probability of x equals 1 is p, and probability of x, there's a mistake here. Probability of x equals 0 is equal to 1 minus p, right? So these are the only two things I have to care about. Everything else is not possible to have. Okay, so what is this like modeling here, right? So what would be a way to think about what this is actually meaning? Why would this random variable be so useful to think about?
So instead of mine fall in 2 categories, like if I pull a card from a deck, there's either a black card or a red card. So lots of different kinds of parts, but it always goes black or red, 0 or 1.
Yeah, right. So okay, so this is a random variable that has an outcome, so that's binary. Okay, so I have basically x goes from some sample space to 0. So between 0 and 1, when there are two outcomes, right? So binary, things, when you have just two outcomes, one bit that you're storing in a computer, right? It's either 0 or 1. There aren't any other possible outcomes, right? It could be corresponding to, if there's a, the deck of cards is either a red card or a black card. It could be, if you, flip a coin, it's either going to be heads or tails, right? So there's lots of cases where there are only two possible outcomes. And so we just want to study the case when there are only these two outcomes, right? You could think of, okay, there are generalizations of this when there are 3 or 4 or 5 outcomes. Then you'd probably want to go back to kind of, so something more complicated, right? But a lot of cases, there are just two outcomes, and we just say, okay, the outcome of 1 heads might be P, some value P, and then everything else has to be, 1 minus P. Okay, this is the kind of, we're starting out simple, okay, but this is a very kind of common case of random variable to think about. Okay, so if I were to flip a coin, right, so a fair coin, right, so if I have a fair coin, so in this sample space is going to be heads or is tails, and I'm going to have a random variable that maps heads to 1 and tails to 0. And I want to describe this with a Bernoulli random variable. I say this is a Bernoulli random variable. What is P? So it's a fair coin. So regular coin, it's not like a trick coin or anything. Yep. 1/2. Yeah. So it's 1/2, right? So in the common case is that it's 1/2. Half the time it's head, half the time it's tail. It's equally likely each of these, right? This is the equally likely kind of scenario we've kind of been dealing with for most of the class so far. But if it's not equally likely, well, then I can change P, right? Let's say I got one of these, so trick coins. So it's twice as likely to be heads as tails. Okay, if it's twice as likely, so let's say trick coin. So twice. So let's say twice as likely heads than tails. So I'm going to say f of x1 times 2 is equal to f of x times f of x of 0, right? So this encodes my heads tails. I have this property. What is P going to be then? Heads is twice as likely as tails. All right, someone over here calculating on your phone. That's what you're doing on your phone? Okay. Well, what's P going to be in this case? What's the probability of getting heads? Let's do it back there. Sure. P is probably heads. So oh yeah. You're right. I wrote the equation down. The way I wrote the equation down, you're right. But I said heads is twice as likely as tails. Yeah, great. So this means P is equal to 2/3. Yeah, great. So if I put in, right, so if I did this, let me say X, so Bernoulli with P, and I said f of x1 is equal to P, and f of x0 is equal to 1 minus p. And I told you f of x1 equals f of x0 times 2, right? So this is why I said it's twice as likely to be heads than tails. This is the likelihood of tails, likelihood of heads. I can plug in p is equal to 1 minus p times 2, and now I can solve for p, all right? So as p equals 2 minus 2p, I'm going to say 3p is equal to 2, and p is equal to 2/3. Okay, and this, let's see if this checks out. Then I'm going to get f of x1 is equal to 2/3. F of x0 is equal to 1 minus 2/3, which is 1/3. And so 2/3 is going to be equal to 1/3 times 2. Yep, and that's right. Okay. So if I said something was twice as likely, well, I know it's only one of those two cases, so I can look at that ratio and I can solve for p. Okay. Yeah, so sometimes you'll just write, so x is, so this like, you know, like, so it's like a tilde, x tilde, or it's like, is from the distribution of, is from a Bernoulli distribution with a parameter p. Okay, so then it's, the x is a random variable from the, which comes from the Bernoulli distribution of parameter p. All right. So, okay, great. So I mean, it's the same thing as if I had actually, you know, just defined kind of heads and tails, and I said heads is, heads comes up with probably 2/3, tails with probably, so 1/3, but it's sometimes useful to think of these like random variables, right? So I could do things like, what happens if I flip, you know, so 10 coins like this, I flip the coin, so 10 times, kind of, let's think about how many heads I would get. Okay, if I flipped a coin like this 10 times, how many heads would I get? Okay, and you can start to analyze that question, right? You know, so that makes sense. If it's a fair coin, the number of heads I get is between 0 and 10. And you could think about, okay, what's the probability I got 4 coins? Okay, so I start with a like Bernoulli random variable, then I could do repeated events with it. It turns out this is another type of random variable, which is the next one we're going to talk about. Okay, so the next sort of random variable is going to be a binomial random variable, okay? And a binomial random variable is now going to have 2 parameters p and n. Okay, p is going to be a probability, like I have a coin I flip, and n is going to be the number of coins. Okay, I flip. Okay, so to define this, I'm going to need a couple of other things you probably, if you've taken a discrete math class, you've probably seen before, but let me just make sure I define these. So this can be like, so to write down, so the PDF, yeah, so let's say that, all right, so if I have an x, a random variable, from a binomial distribution, okay, and I'll say from NP, this talks about the kind of in English, it's like the number of times, instead of writing this, let me just write number of times an an event repeated n times is true with each event true with probability p, right? So I have n of these Bernoulli random variables, and I'm going to add them up. So I could think of having, so the first way of thinking about this, I'm going to have x1, x2, xn. Each of these is going to be a Bernoulli random variable with p, and then x is binomial np, where x is going to be equal to the sum I equals 1 to n of xi. Okay, so this is what I was talking about. You had this random variable xi, right? Each of these was a Bernoulli random variable. And remember, it's this function from a sample space to some value. But what I want to do is be able to add them up. I want to add up these values. And that gives me a new random variable, which is this binomial random variable. I'm counting, and it's 1 if it's true, it's 0 if it's not true. So if it's 0, it doesn't add to my count. If it's 1, it does add to my count. And this is what a binomial random variable is. Okay, so this is what it's modeling. If I flip a coin that's heads with probability p n times, how many times is that coin going to land on heads? Right, if I flip it n times. Okay, and I can model it this way. Yeah. So correct. Right, just like a Bernoulli random variable is either 0 or 1, the binomial random variable will take on values between 0 and n, and it has to be an integer. Right? Again, that's a subset of all the real numbers, but I don't. Okay, so it'll be useful to keep that in mind, but the fact that the real numbers means I can take order, I can add them, I can subtract them, stuff like that. All right. Okay. So I want to define the PDF of the binomial random variables. Okay. To define it, I need to kind of walk through a couple things. We have to remember factorial. Okay. Remember, so factorial, you put an exclamation point after it. It means you're very excited about n. But it's also it's a mathematical kind of symbol that means n times n minus 1 times n minus 2 ... times 2 times 1. Okay, so I'm taking the product of all the integers less than n and n, right? So I could write this as a product, kind of like an uppercase pi, okay, from I equals 1 to n. Think of it like a sum, but I'm just of all these terms I, right? That's what, like n factorials, okay? I need n factorial because I need to define this choose operator. So choose, if I do n choose k, okay, so this is, I have n items, n distinct items, right? I have n different balls, each one a different color, and I choose k of them. How many different combinations can I get? How many different combinations of colors, right? So this is given n distinct balls, how many different subsets of size k. Okay, so that's what n choose 2 means. Seems like a convenient thing. And there's an equation for n choose k. For n choose k, the equation is n factorial divided by n minus k factorial times k, so factorial. Okay. Okay, so it's got a closed form answer for this, but it's kind of messy. If I told you what is 100 choose, so like 20, it would take you a while to, actually do this, sort of calculation, right? You could do it. I could ask you to do it, but that's what's great about using languages like R, or just using kind of as people who know how to program. You can compute this by programming it instead of writing out by hand. Okay, so that's what we'll do, and we'll do that in R on Thursday. Yeah. Yeah, a lot of your, if you have like a scientific, so calculator, probably even on your phone, if you have an app, there's probably a way to do like to compute this on your phone. The numbers can get pretty big, pretty quickly. You can imagine n factorial, right? This is for 10 factorial is like 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. That's a pretty big number, right? So and you're dividing by another big number. They're all so going to be integers. So this is rational, but it's and in fact this has to be so the number has to be an integer, right? Yeah, because it's the number of ways you can choose the subset. Okay, so even though you're dividing one integer by another, it's always going to be, the outcome's always going to be an integer. Okay. Okay, so let's not worry about exactly what to think about this. Well, we can do a small example, like let's do 5 choose 3. Okay, so I have 5 different color balls. How many ways can I choose 3 of them? Okay, so that's going to be 5. So factorial. 5 factorial is going to be 120, right? And it divided by n. So let's see, 2 factorial times 3 factorial, right? 2 factorial is 2, 3 factorial is 6. Okay, so it's going to be divided by 2 times 6, which is 12. It's going to be 10. Okay, so doing 5 choose 3 is not so bad. Okay, but you can imagine if the numbers are bigger, you're not going to want to always do these calculations yourself. Okay, so this, I need to define this partially because it's going to show up in the closed form definition of, so the PDF of a binomial, so random variable. Okay, and so I'm going to say that okay, so now that I have these for a binomial random variable, NP, X is from here, I want to say the PDF of X at a value of K. Okay, this is defined for K, has to be, I'm only going to define this for K in 0, 1, 2, up to N. Okay, so all right, and I can write this as an expression for all of those values. Okay, it's going to be n choose k, okay, p to the power k times 1 minus p n minus k. Okay, so, and then for f of x for k prime, for k that's not in 0, 1, 0, 1 up to n, f of x k prime is going to be equal to 0. All right, so what is it saying? It's saying the probability that I flip a coin n times, and the probability it's heads is p. The probability that it shows up heads k times is going to be this expression. Okay, so this is kind of the key thing to remember here. Okay, so why is this the right expression? Okay, okay, answer. Oh yeah. So okay, what this is saying is I have a coin that is heads with probability p. I flip the coin n times. What's the probability that it lands on head k times out of n? And that's what this highlighted pink expression is. So it's going to give me the answer. Okay, this value, right, n choose k can be pretty big. Remember, 5 choose 3 was 10. Let's say 10 choose 6 is probably, pretty big, but this value has to be, right, this value has to be between 0 and 1, right? It can't be larger than 1, even though n choose k is a number which is pretty big, right? So, so maybe you don't believe me that this is the right answer, because we went through what the choose operation meant, and that gave you a large value, much bigger than 1. But these terms, right, remember p has to be between 0 and 1, and 1 minus p is also between 0 and 1, and we're taking those to some power. When I take a value less than 1 to a power, it gets smaller. Right? So let's say p was 1/2 and I raised it to the power, so 6, right? That's 1/2 to the 6, right? So that's a really small number. So the green part gets smaller faster than the choose part gets so larger. Okay, so that's why it's always going to be an answer between 0 and 1. All right, so let's kind of break this down. Okay, what is p choose k? So this means that this is the probability that I flip the coin k times and all of them are heads. Okay, this is the probability that I have k events all so true. Okay, so I wanted k out of n to be true, so I need to look at the probability that, say, I choose k of those events and those k are true. Okay, so that's what this counts for. 1 minus p to the n minus k is going to be the probability. This is so similarly, right? So the probability that n minus k events are all so false, right? All these events are false, right? Remember, true is equal to 1 and false is 0. Okay, so that's what this is accounting for. So I said, so I could say, what's the probability that I flip 10 coins, right? So let's say 1 coin, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I said the first 6 of them are, the first 6 of these are going to be true. 1, 1, 1, 1, 1. The first 6 are true. The last 4 are false. Okay. So this is true with probability P, with probability P, probability P, probability P, all of, right? And then these are all true with, they're false with 1 minus P. 1 minus P. 1 minus P. Okay, so these are the individual probabilities. When I flip a coin, it should be independent of the other flips of the coin, right? So the probability that all 10 of these events turned out the way I want them to turn out is the product of all of those, so individual events. Because of independence, I can take the probability and I can break it down as the product of the individual events. And so to get the total probability is just this kind of, this product, P times P times P times P times P times P. Wait, this is 6 true, and these are 4 false, right? Times 1 minus P, 1 minus P, 1 minus P, 1 minus P. Okay, right? And I can write this more compactly as P to the power 6 times 1 minus P to the power 4, right? And so that's what I'm getting here. If K is equal to 6, then N is equal to 10, then N minus K is 4, right? So I get 6 and 4 in the powers here. Yeah. Yeah, so there's implicitly an independence of each of the coin flips that I can decompose the total probability that these 10 different outcomes of all the 10 different flips of the coin, that those are all independent of each other. I want all those to be true, so I want the intersection of all those events, but they're independent, so I just write out the product. This is kind of the power of this independence assumption allows me to do this. If they were not independent, then I would, then it would be a lot harder to kind of try to understand this, right? If there was some like gravitational force, like a magnet or something messing things up, and I didn't know that, and I had to learn that as I went, then the first one being true probably influenced the second one being true, and this would be much trickier to try to do. Okay, but I'm assuming that they're independent, and I know the probability P. Okay. Okay, so why is this answer right here not the probability that I flipped N coins and I got 6 of them heads? I flipped 10 coins and got 6 heads. Why is this not the right answer here? Okay, in front.
So you have, what is it,
Yeah.
The issue is that you can order these in all sorts of different ways. So every instance of you achieving what you saw over there has many permutations.
Yeah, that's right. Okay, so I drew this picture, right? This picture right here where I have these different events, and I said for this to get 6 heads, I need 6 of them to be 1 and 4 of them to be 0, right? And that's what I got in the scenario. But I specifically said when I wrote this down that the first 6 were heads and the last 4 were tails, right? But I could have had 6 heads where I swapped, I could think of kind of swapping this one and this one. If I put a heads came later and a 0 came earlier, I would still have 6 heads, right? So I could have any choice of 6 of them are still going to be heads, right? And so the number of ways, so this ends up the number of different ways I can order this where I have exactly 6 ones is exactly 10 choose 6. Okay? If I think about this, think of each of the coin flips as a different color of ball, and I'm choosing 6 of those balls, right? And so any subset is distinct. The 6 ones I choose are where I put those 1 bits. Okay, so how many different ways can I choose 6 balls, or can I put the 1 bits? That's exactly this n choose k, right? This 10 choose 6. Okay, so that says, well, I could get this in any different way, and these are different events in the sample space, right? I'm going to have a sample space of all the coin flips of size 2 to the power 10, right? Each coin could be one of 2 possible things, and I'm going to have, so I take the product of all these things. Remember, we did this diagram with dice where it was 6 by 6. That was rolling 2 dice. If I rolled 3 dice, it'd be 3-dimensional. This is like a 10-dimensional thing, but it's only 2 things wide. So it's 2 by 2 by 2 by 2 by 2, 10 times. So that's 2 to the power 10 sample space. And each of those outcomes, right, is an independent outcome. So I can add those up. So each of the outcomes has the same probability, which is highlighted here, and they're disjoint outcomes in the full sample space. So I can add them up. And how many do I add up? I add up n to the n choose k of them. And so I can they're all the same probability, so I can just multiply by the number of them. And that's how I get n choose k times p to the power k times 1 minus p to the power n minus k. Okay? Okay, so I hope this mostly makes sense. But this formula, you're going to have to solve for this formula when I say, okay, what's the probability that you have 20 coins and they're heads with probably 2/3, and I want to know the probability that 13 of them are heads. Okay, if I ask you that question, kind of this calculation is going to give you the answer. Okay, and okay, it'd be kind of onerous to work through the calculation, but if you use R, we'll see on Thursday, you just put the numbers in and pop, right? We don't even have to program this. This is built in, as we'll see. Okay. Yes, 6 and 4 were just arbitrary choices. Yeah, just for this example. But in general, but 6, yeah, the question is 6 and 4 arbitrary. They were with respect to n being 10, so 6 plus 4 had to equal 10. Okay. Okay. All right, I want to do one more distribution that was going to show up on your on stuff your learning outcomes, and this is the geometric, so random variables. Okay, I'm a big fan of like geometry and thinking of things spatially and stuff. This geometric more has to do with is that something indicates polynomial that's called like a geometric kind of process. So there won't be cool pictures that goes with this random variable. Well, we'll draw plots later, but that's not as exciting. So we're going to think about a random variable from a geometric distribution, from geometric distribution, and this only has one parameter p. Okay, so like the Bernoulli with one parameter p, but this one's a little bit more interesting than Bernoulli, and this one has the PDF f of x of k is going to be 1 minus p to the power k minus 1 times P. Okay. So I don't have to use the choose operator. It looks kind of similar otherwise. What is this random variable so representing? Let's look at the formula. See if you can figure out what's the way to describe in English what this random variable is representing. Okay. Yeah, so great. So let's say there's a coin. There's a coin, or there's, so some sort of event, right? There's some, there's an event with probability P of success. Okay, so there's think of like a coin that's heads with probability P. Okay, what is this describing? So okay, yeah, so K shows up here, and I'm going to get one success out of K chances, right? So I'm going to have K chances. It's not quite right, but you're getting closer. K chances, and we're going to have one success. Okay, but there's something more specific about it. Remember, I don't have the n choose K up front here, right? The n choose K said, well, I could reorder these lots of different ways, right? I'm going to have K minus 1 failures, right? This is where I get failure, and there's K minus 1 of these, and then there's one successful time. Okay. Sure, yeah, that's a perfectly reasonable way of thinking about it, but let's read it from left to right. Can you restate what you said? Yeah, okay, and the success comes at the end. Right. So, okay. So let's think, okay, so this is a perfectly reasonable way of describing it, but there's kind of a more useful way of thinking about it. So let's say no one can leave the classroom. I've got this coin I'm going to flip, and it's going to be heads with probability P. And I'm going to have a coin I'm going to flip, and no one can leave the classroom until I get heads. Okay, so what does this tell you? Yeah, it's the number of times until the first success. Right? Yeah. So don't worry, you can leave anytime you want. You aren't actually stuck here. But it's the probability it takes K so events until the first until the first success, right? So it's all right. So this is often used when the probability of failure is like not very high. This is when it's interesting, right? So like, let's say instead of flipping a coin, I had to do something so like more challenging. Let's say I have to flip the marker and it has to land exactly, it has to land, so exactly like this. So it's exactly straight up and down, right? The probability of this happening is, pretty small. All right, so it could take you a long time until you got to leave. Maybe it's less than, maybe the probability is like 1 out of 1,000, right? So what's the probability that you leave it takes me 1,000 flips before you can leave, right? What's interesting, might be useful is the cumulative density function, right? So the probability I get at least one success in the first 1,000 flips, right? So that would be the cumulative density function, right? Of all the successes that could come first, right? That as soon as I get one success, we can stop, right? So I would take all these and I would add them up for all values k, right? So the CDF, right, is going to be of k is going to be the sum of k prime equals to 1 of f of x of, so k prime, right? And again, if I were to tell you to calculate, the CDF of this, it would be kind of onerous to do the calculation. But with R or some other programming language, it's going to be it's going to be easy, right? You're just going to, type in this one command, it'll give you the answer. So, okay, great. Let me just summarize. We're going to kind of, we're going to have these key parameters, okay? They're going to be common to these kind of discrete sort of distribution. N is going to be the number of trials. K is going to be the number of successes or first, or the first, so success, this is in binomial, this is in geometric, and then kind of common to both of these and also the Bernoulli is P. This is the probability of success. Okay, so we'll stop here. So make sure to finish your homework 2 turned in tonight. Kind of reread the questions one more time and kind of make sure you think you've checked your answers and you're a little bit more careful and so turn those in. And then we'll see how to do all this in R. This will be our first day of R on Thursday.